Hi, everyone. So I'm going to walk through questions 51 through 61 for chapter 3. Um, each question builds on the question before it, um, and each of them, there should be three different questions to do. So I'm going to help you out by doing the first one, which happens to be the easiest one. So hopefully if you're having trouble, you can watch me do the first one and then apply what I've done to the first chemical to the next chemical. So if you look at number 51, the question is to calculate the molar mass of the following substances. And then it gives you uh, essentially a picture of a molecule. You have to figure out the formula from that. So you have to notice the nitrogen is the big blue molecule, and the hydrogens are the little gray ones. And if you look carefully, you can see that there are three gray hydrogens and one blue nitrogen. This is a very common way the AP test likes to ask questions. They like to have lots of um, pictures and models and for you to be able to see to figure out spatially what the chemicals are. So it's clearly made up of one nitrogen and three hydrogens. This, by the way, is ammonia. Okay, one nitrogen, one mole of ammonia would contain 1 mole of nitrogen. When we look up nitrogen on the periodic table, it weighs 17 grams. Hydrogen essentially weighs 1. Technically, it's 1.0008. I'm quite okay, and I recommend that you round hydrogen to 1 in all of these. And there are 3 moles of hydrogen for every 1 mole of the whole molecule. So therefore, 17 plus 3 is, sorry, that should have been 14. 14 for nitrogen plus 3 is 17. So there are 17 grams in a mole of ammonia. And you're going to use that number over and over again over the course of the next ones. So 53 now says, what amount in moles of compound is present in 1 gram of each of the compounds from 51? So essentially what 53 is saying is if I only had 1 gram of ammonia, how many ammonia molecules would I have? Well, we just learned there are 17 grams in a mole. So I have 17 grams in 1 mole. I don't have a whole mole. I only have 1 gram of it. So 1 divided by 17 is 0.0058235294. That's what my calculator says. But remember, I'm smarter than my calculator. I recognize that 51 gave me 1 gram as 1.00, three significant figures. So my answer should have 3 significant figures. So I'm going to call it 5, 8 moles of ammonia. Cool. That's the answer to 1/3 of the answer to 51, and that's 1/3 of the answer to 53. Now you have to do it again for the chemical B and the chemical C. Cool. 55 says, what mass of compound is present in 5 moles? So notice from here, I'm going from grams to moles. So if I can go from grams to moles, then I should be able to go in the other direction. So if I'm given 5 moles of it, how many grams do I have? So notice I'm using the same conversion factor, I'm just flipping it. There are 17 grams in 1 mole, and I have 5 moles of it. So I have 17 times 5, I have 85 grams. And notice again, I'm being careful to make sure I show my significant figures. Cool. I go on to 55. Sorry. Yeah. 57. What mass of nitrogen is present in 5 moles of each of the compounds from 51. So notice it sounded like exactly the same question, but it's not. Now it's asking only for the nitrogen that was in it. So if I go back to the beginning, I notice that 1 mole of the whole thing only contains 1 mole of nitrogen, and 1 mole of nitrogen weighs 5 grams. So, or weighs 14 grams. So if I have 1 mole of this, I have 14 grams of nitrogen. If I have 5 moles of it, well, there are 14 grams of nitrogen in every 1 mole of the whole thing. Cool. So I have 14 times 5, 70 grams of just nitrogen. Cool. If I go on to 59, it says what number of molecules or formula units are present in 1 gram of each of the compounds in exercise 51. Well, notice I already had 1 gram of it. I turned 1 gram into 0.588 moles. Technically, that's kind of the answer, but it's not. If they're asking for molecules or formula units, they want you to take it 1 step farther. I have 0.0588 moles of ammonia in 1 gram. The definition of a mole is that a mole is made up of 6.022 times 10 to the 23rd molecules. So notice you really kind of want to think about what unit it is specifically asking for. It's not asking for moles anymore, it's asking for molecules. So we have to take it that 1 step farther. So it's 0.0588 times 6.022 times 10 to the 23rd. So if I multiply this number by this number, I get 0.354, the 3 significant figures. And then I can just bring down my 10 to the 23rd, right? That's got 1 too few, one, it's not quite the right number of, for scientific notation. So I need to move it 1 to the right. So it's 3.54 times 10 to the 22nd molecules. Cool. All right. That gets us through number 59. I'm hoping you're starting to see the pattern. What are you starting with? What are you ending with? What are you using to convert it? If we need me to go over a few more, I will, but I'm hoping that's enough to help get you started. Hey everyone, I'm going to give this a shot. I've had a couple of questions about number 44 on chapter 3, so I thought I'd do a quick little video of it, get you started on it. So the idea is you're supposed to use the data to estimate the average atomic mass of iron. Well, the simple answer to that is immediately 56. I know that sounds too simple, but the idea is they're only asking you to estimate it. And the biggest peak in the on the graph is at 56, and it represents, if you look at it, 91.75 out of the relative amount of 100 atoms. So essentially it's 91.75% number 56, which means the vast majority of it is close to that. There's a little bit less than it, and there's a little bit more than it. So you could estimate it to be around 56. And there's a little bit less than 56, so you might say it's going to be a little bit less than 56. So let's pretend that the question actually asked you to calculate, based on these numbers, what the actual value of the isotope was. So you would treat those as what they are, percentages, and you would say, okay, If it's 91.75% 56, the percent as a decimal is 0.9175. Multiply that by its mass, 56, and that's going to be the amount that's contributed to the isotope's mass based on how much there is. And then you would have to do that again for the 54. It represents 5.85% or 0.0585. And you do it again for the isotope 57, and you do it again for the isotope 58, and then you would simply add all of those together, and that would be your actual atomic mass. And you're going to see, based on, if you consider these to be exact numbers, then you would base it on 3 significant figures or even 2 significant figures. And then again, it would come out to 56. Or if you thought 3 significant figures, it would come out to about 55.9. I hope that helps you understand that question. I really just did this to see how this video would work. Have a good one.